Okay, so what I want really to do in this last talk is to say a little bit about turbulent flames, particularly premix turbulent flames. But before I do that, I admit that unlike some of the other lecture, this is primarily my group work. And unlike, I want first of all to classify the work relative to the other work that exists. So I am trying more to understand turbulence from a theoretical perspective. Now I want to explain what I mean by a theory. You see, theory didn't quite or doesn't quite exist, or it's very limited. And I want to explain that first. So there are different ways of approaching turbulence. The one which is the most accurate and the most best way, or the most faithful way, is to use what is referred to as DNS, direct numerical simulation. Now, people use the word DNS very often when they do calculation, they would do DNS, but that historically, at least in the fluid mechanics community, DNS referred to doing calculation where you are resolving all the scales, from the smallest Kolmogorov scale in turbulence to the higher scale. And this is very difficult because it's time, as it's described here, it's very difficult because it requires computational resources that are not, in fact, available. I don't want to run through, this is part of chapter of lecture 14. I'm not going to go over it, but I want to just pick on a few things, and then I want to move to 15. So DNS is being used for fundamental theoretical turbulence studies in a limited way because of the high computational cost. It's not a feasible tool to study, say, parametric study. You can only study very specific condition. And it also, you can only solve very small scale problem, basically. There is, of course, other approach. I'm not going to run through the detail of this. You can read it and probably understand it quite easily. It just gives you an estimate of what it takes to solve a problem. And it's taken from the book by, this table is taken from the book by Steve Pope. It just shows you that if you want to solve something which with a turbulent Reynolds number, which is where turbulence occur, it might take a huge number of years. So really, it's not very feasible to solve large problems. Then you have the more traditional turbulent, what is often referred to turbulent modeling, where you use RANS, so you use averaging. In other words, you decompose every variable into the mean plus a fluctuation. And you write the equation for the mean quantities. Now, for many practical problems in the industry, if you can solve for the mean, it's great. You don't really care about the small fluctuation. Unfortunately, the equations for the mean require what we call closure. In other words, they are terms that you don't know them, and in order to determine them, you have to solve a higher order system, and that higher order is also not closed, and so on and so forth. So there is a closure problem there. And so what people do, they estimate those terms, or they incorporate different models or different ideas. But remember that all these models, they may be working very well in one problem or another. They're not universal. They are just ad hoc, and they fit one or other condition and so on. It's unavoidable for practical problem. I repeat that because That's what it is. I should say, by the way, that, well, I don't have that slide. When I was talking about DNS, what do you solve? Well, the general understanding or the general acceptance is that the Navier-Stokes equation describe even turbulent flow. They describe the flow even at all the scale, okay? The reason that it's difficult to solve turbulent flow problem, it's essentially because the solutions are very sensible or sensitive to a small variation in the initial condition, and so they are not repeatable. A small different initial condition lead to something which is different, and that's why statistical methods are used. Now, in some of this, I have shown the closure problem, but I don't want to, well, you can see here, for example, in a pure Navier-Stokes equation, what you do, you write some effective viscosity for the closure of that term, but then that effective viscosity is not a true property of the fluid, it's just a property of the flow, and you don't know it a priori, so you estimate it, and so on. Anyway, it's some people call this the theory of turbulence, fine, but that's not what I meant when I used the word theory from the beginning. So then you have a PDF transport equation, and they are very difficult equation to solve anyway, and they have also their limitation. Then you have large eddy simulation, where it operates on the governing equation to reduce the range of the scale that need to be modeled like in RANS, but still you have you are filtering the small scale, and you need to write equations, or you have to write to put in something that describes the small scale. And in combustion, small scale is where everything happening. So the small scale models are also ad hoc in some way. So this is really what I wanted to comment to begin with. Then I have in those notes this famous turbulent regime diagram that people have established over the years. It started with Bourgui and Peters, Williams, there are a few others. But anyway, the idea is that there is, depending on the turbulence intensity as a function of the integral scale, the integral scale represents say, the scale of the average eddies in your turbulent flow. And by the way, the word eddies is very often used, even though it doesn't have a precise meaning. It is just a small lump, if you like, of fluid that behave more or less in the same way. And so you have small eddies, large eddies, and you have, of course, the picture that energy is transferred from the large to the small until they get dissipated by viscosity on the small scale. But so in this diagram, there is essentially different regime. I want to talk about this one quickly and then goes down. So in the distributed reaction zone, the reaction occurs basically everywhere in the field. And it's like if it's well stirred. And so really there is no even a flame that can be identified, okay? It's a reaction almost everywhere. In contrast, in the lower end, the wrinkled flame, this is a turbulent flame, but it's slightly wrinkled, and then the corrugated, the corrugation can be larger and so on. And then there are a regime where the eddies are larger than the smallest eddies. If this is the flame, the smallest eddy are of a size larger than the flame thickness, and they therefore don't affect the flame thickness so much. And then there is a regime where they affect the flame, but not the reaction zone, and so on. So these are the different regimes, and I will skip over all this And I want to come to, as I said, it's going to be mostly work that, or it's built on work that that I am involved in. And it's more theory-oriented. In other words, there is no ad hoc, there is no modeling, there is no averaging. We try to take a model, which is going to be, in this case, the hydrodynamic model, which was derived systematically as an asymptotic model, try to learn what we can from that model. It has limitation, but it has also some strengths. So we're going to learn from what we can. And so that's basically what it is. So quickly, you start with what I have put here is just to remind you that in a laminar setting, what you have a flame propagating in a quiescent mixture, and we can identify or we can talk about the flame speed, which is the speed that this flame propagates in the mixture, or the burning speed, which is the rate that the mixture is consumed. And that speed is well defined, and we have seen before all these expression and so on. The question is, can you also define what is a turbulent flame speed? A priori, it's not obvious that there is such a thing. In fact, I just started with a case where a well-steered reactor, there is almost no visible flame, so how do you define a flame in that case, right? So under some condition, probably you can define a flame speed, and it's when you talk about the average speed of the flame into a turbulent flow. And obviously this will apply to this regime like the flamelet regime or reaction sheet regime, but it's less obvious if you go to the distributed reaction regime that I mentioned before. The practical importance of having something like a turbulent flame speed is obvious. It gives you some indication of how quickly you would consume your mixture in a turbulent setting. So as I said, can a well-defined turbulent speed be identified? Experimentally, you see that Bunsen flame, for example, even under turbulent condition, maintain on the average a certain angle, conical angle. And we have seen earlier this week that the angle is related to the flame speed because it's the ratio of the incoming flow to the laminar flame speed is the sine of the angle, right? And so clearly that suggests that there is some kind of turbulent flame speed that can be defined. Also, flame in tubes seem to propagate at a, well, not defined, but defined distance at a given time. Despite that, people experimentally, the data is very, very dispersed. You see the data here, and this was collected over almost 1,600 studies by Derek Bradley early on. Then they tried to put some picture to it or try to collapse some of the data. And eventually, this is more or less what people, what seemed to be the behavior of the turbulent flame speed. It increases with increasing turbulent intensity. What is plotted usually is the turbulent speed relative to the laminar flame speed. In other words, you use the laminar flame speed as reference, and you plot it as the turbulent intensity, which is the RMS of the fluctuation, okay? So in other words, it's the square of the fluctuation velocity, square root. So it's the measure of how turbulent the flow is. And so generally it increases with increasing turbulent intensity, but eventually it slows down. In other words, the rate decreases eventually, something which is referred to in the literature as the bending effect. Okay. So I want to first make again clear what's the definition of the turbulent flame speed before I move on. So what you have, it's a let's say that's a cross-section of the flame. You have a flame here which is turbulent, and it propagates against a flow which is turbulent with zero mean, equivalent to a laminar flame propagating in a quiescent mixture of zero velocity, right? So, but of course this is a difficult setting, so it's more, it's easy to look at that in a reference relative to the flame, where the flame statistically is fluctuating around a position y equal to 0, and the incoming mean velocity is going to be the turbulent flame speed, St. And all the average, the mean of U1 prime, U2 prime, all these fluctuations is 0, right? So there is no mean velocity in the other direction. And so that's the turbulent speed. The first probably significant discussion on this subject came from Damkohler. It's the same Damkohler that we refer to as the Damkohler number, but his contribution was mostly in this respect, and somehow it disappeared from the picture, and I don't know why. And I visited Aachen some years ago, and one of quite famous people in the community was still alive, Norbert Peters. He actually showed me a picture of Damkohler. He found it somewhere, but apparently he didn't live long, and then he didn't contribute more to the science, unfortunately. So anyway, Damkohler identified two distinct limits. He called them small-scale and large-scale turbulence. Today we have this new terminology and this new diagram, but essentially he had the general picture that in small-scale turbulence, the small eddies interact with the diffusion and conduction transport mechanism within the flame. In the large-scale turbulence, the flame is thin compared to the smallest turbulence scale, and so the turbulent flame interaction is primarily kinematic. In other words, the turbulent flame just distort the turbulent flow essentially distort the flame, but doesn't do anything to its internal structure. And this is, and in the small-scale turbulence, that is, of course, it's a phenomenological expression, but basically he said the turbulent speed, the laminar speed is known to depend as the square root of the thermal diffusivity divided by the flow time, the time it takes for the flame to cross the flame. So in a turbulent setting, it's going to be not the thermal diffusivity, but the turbulent diffusivity. And so this way he wrote that the ratio is the turbulent to the thermal diffusivity, but then he had to say what is the turbulent diffusivity. He said, well, it's going to be, since it has units of centimeters squared per second, it's going to be some velocity and length, so it makes sense that it's the integral scale multiplied by the intensity. And so this leads to this expression for the turbulence speed, but this is for the small-scale turbulence. For the large-scale turbulence, which is the focus of what I will talk about today, well, he said the following. Let's do a mass flux balance. The mass flux coming in this cross-section is rho u times the mean velocity, which is st, times the cross area A. So the mean flow rate coming from the bottom into this cross-section is equal to this. And now if all this mass is consumed along this turbulent flame, along every section the flux across some delta A, which is some segment of the flame surface, is going to be rho u times the laminar flame speed, assuming that it is consumed at the rate equal to the laminar flame speed, multiplied by the delta AF, and when you integrate over all the surface, it's going to be the mean area of the turbulent flame. And so when this is equal to that, you can write that ST over SL is the ratio of the corrugated surface divided by the cross-section. So this was Damkohler's idea, which is still alive until today and used quite often, especially by experimentalists, of course with modification, but it is still a very key result, I would say. And the next step that he did, well, he wanted to relate it somehow to intensity, and so he made some argument to argue that in analogy to a Bunsen flame, in other words, he said, okay, when you have this corrugation, one of these corrugations like a Bunsen flame, and try to make estimate and to obtain that the area ratio is going to be like the intensity divided by the laminar flame speed, which at the end means that the turbulent speed is proportional to V prime. Few years later, Shelkin carried out this idea and and derive, I'm not going to go through this, but essentially derive an expression which is built on the same idea that this is the eddy and the area is affected by the V prime divided by SL and so on. But he derived this expression. This is a square root of 1 plus V prime over A. And he argued that my expression is a bit more general than Damkohler because if you assume that high intensity, that for high intensity 1 is negligible compared to V prime over SL, this is squared, you take the square root, the SL cancel, you get V prime, exactly what Damkohler suggested. And when V prime is small, then you expand this in a Taylor series, and the first term is 1 plus 1/2 V prime over SL squared, and so that's what you get. And so he argued that for small intensities, it have to be a quadratic behavior, and for larger intensities is linear. And then if we jump up in the development, the only next significant theoretical development was by Clavin and Williams. It's not FFM, but it's JFM, and I catch my typos. And Clavin and Williams, it's in fact the same paper that I mentioned earlier this week, that they have used the multi-scale approach by looking at a planar flame which is weakly perturbed and so on. And they were able to argue that the turbulent speed versus laminar flame speed is 1 plus V prime square. Again, a quadratic dependence, but no half, as Shelkin had. Actually, an expression of this form is being used quite a bit by many experimentalists and modelers with C and N varying, fitting either experiment or whatever. In other words, those are exponents and constants which are determined using physical argument, phenomenology, and they may depend on other parameters, but essentially. And more or less, this is the state of the art of things in terms of development without what I have referred to before as turbulence modeling and all these other things. So the step that we took is by saying, okay, we're going to modify this idea of Damkohler in the following way. The speed of that flame segment is not necessarily SL, it's not always the laminar flame speed, but it's the local flame speed. And for weakly stretched flame, we know the dependence of the flame speed on the local flow condition, which is stretch, and the Markstein length. So this is the general idea that we have incorporated here. But even without saying anything about stretch and Markstein lengths and so on, what you see when you make the same argument as Damkohler is that the consumption of the local segment is going to be rho u, and then the average of SF multiplied by this delta AF. So when you take the average over the whole flame surface, it's going to be the mean of the product divided by SLA, and it's only true to remove SF from the mean when it is a constant. Otherwise, you may, in other words, what the point is that there are contribution to the turbulent speed other than just the area ratio, and those could come from the flow field and in what we are going to use, effect of stretch and mixture fractions. Just another comment to make is when the flame is folded, and it could be folded in general now, then you have to be careful how you compute this average, because in a given interval A, you may have more than one piece of the flame, and you have to account them for all. Okay. This is the general picture or the idea of what we have been doing. What we want is to bring in here a turbulent flow with some mean velocity to get the flame stabilized at some position, and to ask what is the turbulent speed in this case, which can be computed either from the formula that I showed you before about the area, or from just the fact that the mean incoming flow is a turbulent speed. In fact, we did the calculation both, and both give the same answer, so there is no advantage of one over the other. It's just a backing that you are still doing correctly. So how to do this? So first of all, you generate a two-dimension, well, we have done the calculation in 2D. We are hopefully doing them, or will be doing them soon in 3D. We started. So anyway, I'm going to talk about 2D. So we have a two-dimensional flow, turbulent flow that you generate a priori in a sufficiently big domain. And that's the flow that you're going to feed here at different times. At every time t, you feed another part of that flow. That flow is produced with periodic boundary conditions, so there is no effect of boundaries and so on the turbulent that you are inserting. But clearly the turbulent have properties that you can identify a priori. One of them is the intensity, the other one is the integral scale. So that's what we can control. Now we use a control system in order, I mean, one possibility is just to let the flame propagate, but then you need a huge domain. So it's preferable to have a control system to keep the flame statistically stationary at a location. And we do that with this control that was created. In fact, we can control many things. One of the things we can control is we can control that the result that we are going to present will be a function of the intensity at a location within a certain close distance from the flame. Because very often when you introduce the turbulent flow here, by the time it reaches this distance, the decay of turbulence, and so you are presenting a result in terms of a V prime, which is not really the V prime that the flame is actually experiencing. And we can do other little things like this with the control. So as I said, the turbulent speed will be computed either as the mean velocity coming in or from this extended Darmkohler expression. And the model is what I have described earlier this week when I talked about the hydrodynamic model. We solve the Navier-Stokes equation with different densities, rho u and rho b, across that interface. The flame speed is given by this expression, which depend on Markstein lengths and the stretch rate, k. V star in this expression is the velocity of the unburned, or on the unburned side of the flame. And of course, this problem is highly coupled. You have to solve the equation together all the time. And the parameter, well, we use a level set approach To advance the flame, we use a Navier-Stokes solver for the Navier-Stokes equation, and we use quite careful way of satisfying the condition at the interface, in particular ensuring that the gas expansion is properly accounted for in the problem. The parameters that I emphasized here, so you remember which parameter we're talking about, is the density ratio sigma, the Markstein number, which is the Markstein length divided by the total length scale, so it's the total length of the integration domain, which is not necessarily the Markstein length as reported typically in the literature, because typically we define the Markstein number as L divided by the flame thickness, so you have to just understand that the difference is just the ratio of the flame thickness to the domain. So it's correlated to the known Markstein number. And then you have the turbulent parameter, which is the integral scale and the turbulent intensity. Just to remind you that sigma is effectively the heat release, right? Because it's the ratio of density, so it's a ratio of temperature and so on. So the chemistry or the chemistry or the combustion is all hidden in two parameters, this sigma, which gives you the gas expansion, and this L, which gives, and this L, which gives you the diffusion properties of the mixture. Okay, and I want to remind you that the theory is limited to positive Markstein numbers, so unfortunately at this time we cannot do anything with negative Markstein number, because there really the flame is further distorted by diffusion thermal effect, and at the moment we don't have a theory to properly describe that. This just gives you the key idea of how it was implemented. Zero Mach number, variable density, Navier-Stokes solver, Rankine-Hugoniot condition for were satisfied by appropriate source terms. We advance the flame front using a level set, and we use the idea of immersed boundary to carefully compute the flame flow interaction. It's not very easy to evaluate the value of V just ahead of the flame, because the velocity, as we have learned this week, the normal velocity jump by a big factor, and so if you just try to interpolate to get the value, you get lots of bad things in your computation, in particular oscillation things. So we have to do careful things. I want to say that this is not a trivial numerical problem to do, and because of its complexity, there is no Fluent or anything like this that you just plug in and run. You have to really do your code, you have to build it carefully, and you need good students to do it for you. So this is, here is, we start with, I want to start with showing you a few things. So first of all, low turbulence intensity, and a low and a Markstein number 0.08. Just to remind you that always in this we talked about, well, I'll mention that later, sorry. Does this run? Oh yeah. So here is how the flame reacts to the turbulence. You don't see much in the burn region just because the colors are fading, but you're going to see in some of the picture later. This is a very weak intensity, and the flame is slightly responding to it. And now it's a same intensity, but it's a different Markstein number. Now you see already from the picture here that the flame has this cusp-like shape. Now remember when we talked about flame instability that at the lower Markstein number, the planar flame are no longer stable. So naturally you want to get, the natural flame that you get is one with this cusp-like behavior. And so even when you introduce turbulence, that cusp-like flame is the leading or the flame that you observe typically. Now you see the vorticity. Oh, by the way, these colors are vorticity, blue and red, different direction. And now you see clearly the vorticity in the burn gas. Mostly the intense one come from the peak, from this highly peak that is created. Okay, just to remind you, this picture was the bifurcation picture in laminar condition. It was for the larger Markstein number, the flame was stable, and when you reduce the Markstein number below a critical value, you obtain these cusp shapes, and they propagate at a velocity higher than, those are the stable, the green curve is only the stable flame under this Markstein number. And this is the critical value in case it come about. So just the two pictures that I showed you earlier, for the two Markstein number, now I'm going to show you a flame brush, in other words, superposition of many flame of different times. So you see, as you increase the intensity laminar, the flame would be just flat because we are here. Because it's turbulent, the flame is slightly corrugated, but on the average is flat. And I'm going to convince you soon that it is almost flat on the average. What happens if you change to the Markstein number where the flame is unstable? Even in the weak intensity, the flame want to maintain that peak structure. And of course, as you increase the intensity, well, it's there, but you see it less and less because there's more and more turbulence. And so the picture that I've just shown you before represent what we refer to as subcritical and supercritical. Subcritical are the one that are more smooth-like, and supercritical that have this cusp Landau-Darrier instability. And we would argue that this is a subcritical flame and this will be a supercritical flame. You can easily see this cusp structure on the surface, and here it's the more smooth surface perturbation. Now, how do I really connect it to the theoretical description? Well, it's here. The Markstein length or number the Markstein length is proportional to the flame thickness, and the difference between these two pictures is not so much the intensity, which in both cases is relatively small, but the change in pressure. And so this is at high pressure meaning a lower flame thickness, a smaller LF, therefore smaller L, and smaller L is a smaller Markstein number. Smaller Markstein number is more unstable. So the trend is in that direction. Those are pictures taken from Creta and Troiani in Rome, and they have done this two-dimensional calculation. Actually, maybe someone in the audience have also helped them to do some of those. I won't embarrass anybody by saying names. And so you can see that there is a more subcritical nature and a more supercritical nature to this. And now if we look at the statistics, because PDF very often tell us more about the nature of the flame, you see that in this case, the PDF are very symmetric, both the position and curvature. It means that the flame has the same tendency, the turbulent flame has the same tendency to have a positive as to have a negative curvature. And so it means that on the average with a zero curvature is nearly flat. That's what we refer to as. Okay, we also looked at the propagation speed as a function, at the turbulent speed as a function of the intensity. And we were able to see that for a variety, we have better, I will show you more important result than this, but this was intended to show just a dependence on different sigma, which is the density ratio or heat release. And you see the quadratic dependence that was anticipated before in different studies. And even it fits with a result of the Michelson-Sierczynski equation, which is an equation derived under the condition when sigma minus 1 is very small, in other words, very small heat release. In that equation, when you add something like turbulence, you also obtain a quadratic dependence, but of course, for small sigma, it's going to be lower than the others, and so it fits very nicely in the general picture. What is of interest is, in this graph in particular, is the dependence of the coefficient on sigma, on the heat release. Not very many results have reported such a dependence. And what we see is there was one paper in Aachen that also reported something similar, that there is an increase of this coefficient with heat release, which you expect that there would be a higher turbulence speed, but due to that coefficient, but it equilibrates eventually. In other words, as you increase sigma below some value, it starts to plateau at some value. Okay. Supercritical condition. What you see is that the PDF, the red one is for the subcritical case, the blue one for the supercritical case. The red one is the PDF of the position, right? You know, the position is typically centered here around half, and it's equally distributed. The flame fluctuates between these two values. But in the supercritical case, the flame is not symmetric, and so it has that peak structure, and so you see the asymmetry of the flame. Also, more interesting is to see the curvature, which first of all, it doesn't have a zero mean, and second, there is some probability to have a negative curvature. Well, because the peaks have always negative curvature, and those are created quite often in your turbulent field. Okay, now the next we want to move up with the intensity. So now it's a higher intensity. Now, higher intensity, the flame doesn't just gently move, but can fold. And when it folds, it can create a pinch. When it pinch, pocket can be created, and so on. And so I believe that's the move, yeah. So you see it folds, it creates pocket. The pocket here, it's pinching. The pocket is here still, very quickly consumed. Keep on doing this. By the way, the movie here was slowed down so that you can see better. It's not slower, it's a higher intensity, but it was intentionally slowed down. Okay, so when you go to higher intensity, if I put if I look at the flame brush that I was talking about before, this is what has been added. In other words, now it's very hard to identify or to argue that the flame is strongly affected by the Dario-Landau instability or not, because turbulence seems to be dominating. Okay? It could be that the Dario-Landau instability is still there, but it has a less of an influence on the overall flame. And this is another way to see it. Those are the PDF of location and of curvature and location. And as you increase the intensity, they start, you see the green one, just a minute now, the red is the subcritical, so the red are more or less always symmetric, okay? They are wider because the flame brush gets thicker and thicker when the turbulent is higher, but they are basically symmetric. The green one here are the supercritical flame, where you have these peaks that create this negative curvature, but eventually, when turbulent dominate, they become again symmetric. And if we have gone here to higher intensity value, presumably the two will be very similar. Okay, they tend to that, but they will be. Okay, so this is, in fact, is a picture that shows the flame brush, and what it shows is the thickness of the flame brush, or the delta T, if you want. And you see that it vary originally, but eventually they seem to converge, meaning that they will be independent of if it's in other words, the two subcritical and supercritical will seem the same. Okay, I'm going to rush through a few things because I want to finish more or less on time. So the turbulent flame speed, and I want to emphasize only things on the turbulent flame speed now. This is a result of the calculation. What we see is that at low intensity we have a quadratic behavior, okay? And this, we have gone through intensity up to 3, but eventually, hopefully, we'll be able to do that. That already takes a long calculation time, and we are limited in computational facilities. So that's what you see. And then at higher intensity, you see that it's no longer quadratic, but it's a sublinear. The exponent here is less than 1. Okay, so there is a tendency the turbulent speed slow down as you increase the intensity. Now, the next picture will show not only the turbulent speed, but also the area ratio. And the idea here is to show you that the area ratio is not exactly the turbulent speed. There are apparently effects that are not in the area ratio. The area ratio gives you a larger speed than what the turbulent speed is, okay? And the exponents are larger. So at low intensity, it's still quadratic. At high intensity, it's sublinear, but here with n point around 4.4, here is much lower. You can also see in this picture the Darry-Landau influence. First of all, I didn't mention this when I show you the graph before, but note that the blue curve and the black curve don't go to 1. Often people try to force them to 1, but that doesn't seem correct, certainly not in our case. When the intensity go to 0, you would say that the flame go to a laminar. But for laminar condition, the subcritical and supercritical propagate at different speeds. The subcritical flame is a planar flame and propagates at the laminar flame speed. The supercritical flame is a peak structure that propagates faster. And so you see that the curve here goes to the value that should be from the bifurcation diagram that I showed you earlier. So this enhancement here is due to the Darry-Landau instability. Similarly, the effect here is due to the Darry-Landau effect, which tend to minimize as you increase the intensity, as I showed you earlier. So if we analyze this a little bit, we can argue that the turbulent speed is the area ratio, but with this stretching factor. And the stretching factor has an effect on reducing the exponent. I'm going to run through this faster and just show you one more or two more things. This is a set of flames at different time, consecutive time. I have chosen this just because it's a set of times where the flame is being folded, it pinch, it creates a little flamelet that is detached, and that little flame is consumed very fast, and then it's not there. And now I'm showing you what happened during that event. During that event, the turbulent flame speed increases. Of course, the surface area also increases. Note that the surface area is larger than the turbulent flame speed increase due to the stretching that I mentioned before. And then after the small flame segment that detached from the flame has disappeared, then the flame speed drops. So what we argue is that it is this frequent folding of the flame and detachment that cause a reduction in the main flame speed surface. And that is the main reason, in our opinion, of the bending effect that caused the turbulent speed to eventually slow down as you increase the intensity. We have curves like this for a variety of Markstein lengths, and the key thing was to construct, the next step was to construct scaling laws. In other words, to see if we can put all this data into some universal function. And we have two scaling law, one for low intensity, which is shown here, and the next slide will be for higher or moderate intensity. So what we argue is that turbulent speed would have a stretching factor that of course depends on the property of the mixture. You see, there is no ad hoc coefficient. Everything is given a certain mixture. I can tell you what is the Markstein length, and I can compute this average stretching from the calculation, because the average stretch or the mean stretch is something that you compute in the Navier-Stokes flame level set calculation. And then you have these coefficients which are indicated here, and you indeed have a quadratic dependence on the coefficient. And of course, these also depend on the heat release, or sigma, as I have shown you earlier. But this is one. And then for moderate turbulent intensity, we see different scaling for the supercritical and the subcritical. And note that all our data for all the Markstein lengths, all the sigma that we calculate, everything fall into that scaling law. So the scaling laws seem to at least represent the data in this range quite accurately. And again, we see a stretching factor, but now a sublinear dependence on intensity, which is a result of this bending, or which is the bending effect. What I have just shown you is quite similar to what have been shown experimentally here at Princeton by Professor Law and some of his collaborators. They have looked at experimentally at a spherically expanding flame and tried to correlate what you see here is exactly the turbulent speed. And even though you don't see exactly what they have here, I rewrote it. So it's the intensity divided by the Markstein length divided by the radius. The radius of the flame will be equivalent to like the length of my domain, and therefore it's my Markstein number. Now clearly the range here, it's up to higher intensity than what we have. It goes to 15, 20, and so on. And I cannot argue that the same, exactly same exponent, because clearly on a different range things can slightly be different, but it has the same character or the same behavior. And and one can also compare this with the result of Kobayashi that presented the result in terms of pressure. Again, you see his turbulent speed as functional laminar speed, and here is the pressure ratio to some power. Now remember that the pressure ratio, it's related again to my Markstein lengths. It's the reciprocal of that. And so we can, I think there is a typo here, but I'll check it later. But anyway, the idea is that we have the same kind of behaviors. Okay, it's just about time to wrap up, so I want to make few comments. First one is just about what we just show here. The asymptotic theory, whether in the laminar case, but in particular in the turbulent case here, assume that the flame is thin. All the mixture property are lumped into these marks, into this parameter that we call the Markstein length. Based on physical principles, I mean, what I mean is the model is based on physical principles, is derived fundamentally from the equation. does not depend on any turbulence modeling assumption, any ad hoc adjusting coefficient, or anything like this. You're giving me a mixture, I compute L, I run the turbulent code, and here are the results. They agree, they don't agree, we ask why, but that's it. Of course, and for the turbulent speed, we were able to derive scaling laws, and they seem to have the same trend as the experiment. We have examined successfully effect due to area ratio, stretch, mixture composition, pressure, and so on. And in particular, we have discussed to identify the importance or lack of the Dario-Landau instability, which has been always questioned in turbulence studies. Of course, as in every theory, it has a limitation. And the limitation is that there are missing effects of the turbulent effect on the internal structure. The idea is that the internal structure remain like the laminar flame structure, and this may not be true, at least certainly not in situation where the turbulence is affecting the internal structure. Also, we have so far discussed 2D, and frankly, people in turbulence tell you that there is no such thing as two-dimensional turbulence, which is probably correct. But there is a lot of things that we can learn from here as we are moving into the 3D. There are things, for example, like vortex stretching and so on that exist in turbulence but are not in 2D. And the question is, how are these important? But when you do 2D calculation, and that's a view, an applied mathematics view, if you do 2D calculation, then tomorrow you do 3D, and you look at what is the effect of vortex stretching, you will understand exactly what vortex stretching does. Without that comparison, it's only a speculation. The other thing that I would say about 2D that is problematic, it's because it's known that in 2D there is a reverse cascade, but this is probably true, but I don't think it affects these results because it's not in the range of what we are talking about. But this is for a different discussion. Finally, we are limited to positive Markstein length, and this is a limitation of the theory, but I told you earlier already this week that there are limitations that we should eventually address. So throughout this course, I try to show you, first of all, the diverse phenomena, the complexity of the subject, the multidisciplinary of the subject, the need of simple models to try to understand things. It's very difficult to throw things on the computer, get huge data, and then what do you do with it? Or you see certain changes and you ask yourself, okay, why? And through simple model, you understand certain phenomena, and then you try to put them together to understand more complex picture. And so I want to finish with just comments that were made by a well-known philosopher, William James. He lived in the 1842 to 1910. And is actually well known for his book, The Principle of Psychology, which is still, I understand, being used in teaching psychology. And what he said is the following: the first response to a new theory is that the ideas are wrong. The second, or later, when the ideas are found right, the response is that they are unrealistic or insignificant. And finally, when they are accepted that they are probably right and important, they say, well, it was obvious, it's all known. And with that, I want to tell you thank you for your attention during the week.